Hello, physical science students, and today we're going to look back at a little snippet of history. In 1665, Isaac Newton, we talked about him yesterday, was a 23-year-old student at Cambridge University in England, and the university in 1665 closed for a period of 18 months, about a year and a half, due to the bubonic plague. During his little break, Newton ended up using that time to develop the law of universal gravitation, calculus, and 3 laws of motion. Pretty amazing, isn't it? We already talked about the law of universal gravitation. We are not going to do calculus, although you should know calculus is a very important tool in helping us to describe motion and describe things in physics and in science, but we're not going to do it. And we are going to talk about Newton's 3 laws of motion. In this section, we are just going to address the first and second laws. So let's start by looking at Newton's first law of motion. An object in motion tends to stay in motion, and an object at rest tends to stay at rest. You should all have heard these before. This picture is a little bit of an illustration of aspects of this first law of motion. This man's face, if we could think of it as being an object at rest, it's going to tend to stay at rest unless it's acted upon by an unbalanced force. This fist right here is certainly delivering some unbalanced force to this man's face. He will probably end up moving that way. So it tends to stay at rest unless acted on by an unbalanced force. Likewise, if an object is moving at a constant velocity, it will continue to do so unless it's acted on by an unbalanced force. You could kind of think about this man's arm moving through the air. It is certainly acted on by the unbalanced force of this man's face, exerting a force this direction. You might also think this is strange because things do end up, say, even if you play pool, when the pool ball is rolling along, eventually it comes to a stop. Or if a ball is rolling along, eventually it comes to a stop, right? Or things do stop at some point. So how can you say they will continue going at the same velocity? Well, remember when we talked about friction. Friction is a force, and it is acting against the direction of the motion. In the cases that I just spoke of, we have friction acting in an opposite direction from the force of those moving objects. So remember that an object will continue at a particular constant velocity unless it is acted on by an unbalanced force. So this tendency of an object to resist change in motion is called inertia. And sometimes Newton's first law is called the law of inertia because it deals with the object resisting change in motion. These are all examples of inertia, objects resisting change in motion. Right here, we have objects traveling this direction. We have the cart and all the objects in it are traveling that direction. Suddenly, everything encounters a force because it bumps into this object right here. The force from that object is being exerted. And that's being exerted in the opposite direction. However, some of these objects, like this one right here, is not feeling the effects of this force. It continues to move in the direction that it was moving initially, this way. And it falls out, kind of keeps going over the top. We can see clearly that inertia is going to affect those girls on the lawn. Kind of a funny picture. And here's just an example of how if you pull that paper out fast enough, this object is at rest. That coin on the top should stay at rest as long as it doesn't really feel the effects of the motion of that object being pulled out from under it. So which object has the greater inertia? This bicycle or this van? Well, it's probably intuitively obvious to you that inertia also has something to do with the mass of an object. If you take an object like this, it has less inertia. It is requiring less force by this woman to move that object, whereas this has greater inertia, and it is going to require a greater amount of force exerted by this woman in order to move this object. So mass definitely has something to do with inertia. The greater the mass, the greater the inertia. And that is true whether it's still or whether it's moving. In these cases, these women are trying to move these objects, but it could be the same for trying to stop the object as well. The greater the inertia, the greater the mass, the greater the inertia, and it takes a greater amount of force to change its motion. Sometimes people say an object, when it moves, it overcomes inertia, and that is not an accurate way to describe what's happening there, because inertia is simply resistance to the change in motion. So it could be any change in motion, whether it's starting, stopping, turning, bending. And that brings us to Newton's second law of motion. And Newton's second law of motion, it states that force, mass, and acceleration are related. Let's explore how these three things are related. First, let's look at force and acceleration. How are those related? Well, we have two pitchers here. They're exerting different amounts of force, certainly. Which pitcher is exerting a greater amount of force on that ball by pitching it? Well, I hope you said this one. This pitcher certainly is exerting a greater amount of force. Once the ball leaves the hand of each of these pitchers, which one do you think has the greater acceleration? Now remember, acceleration is simply the change in velocity per the change in time. Which one of these do you think is larger? Well, certainly this one is going to have much greater acceleration. Therefore, we know that a greater force being exerted is going to give us greater acceleration. Now let's look at the relationship between mass and acceleration. Let's use kind of a similar scenario here. We're going to talk about a baseball versus a softball. A softball has a mass of about 0.2 kilograms. A baseball, on the other hand, has a mass of 0.14 kilograms. If you exert the exact same amount of force on each of these balls, say you pitch it one time and pitch the other one another time, and you're exerting the exact same amount of force, the softball is going to have a lower velocity than the baseball does, because they have different masses. This difference in velocity definitely directly translates into its amount of acceleration, since the softball experienced a lower velocity initially. It's also going to experience a smaller acceleration, smaller velocity in the end. And so we can see here that mass and acceleration are both going to be related as well. So that brings us to how we get this wonderful equation, which Newton came up with. It's very simple, very basic, and it really sums up the second law of motion. And that is force equals mass times acceleration, and it's right here. F equals ma, where force is the force measured in newtons. Little m is the mass in kilograms. A is the acceleration in meters per second squared. And wow, doesn't this look a lot like that other equation that had to do with the universal gravitational law, where the force due to gravity was equal to the mass times the gravitational constant? Yes, looks a lot like that. Remember, force has a direction. Force is directional. That's really important here too. So let's try a little example here. When a tennis player hits a ball, the ball's velocity changes over such a short period of time that its acceleration could be as high as 5,000 meters per second squared. Wow. The ball's mass is 0.06 kilograms. So how much force would be exerted on the ball by the racket if it were indeed reaching this much acceleration? Let's write down our equation that we just learned, and let's write down what we know. We have force equals mass times acceleration. We are given the mass in this problem. We know it is 0.06 kilograms. We are also given the acceleration possibility here. That is 5,000 meters per second squared. And the question being asked is how much force would be exerted on the ball. So F is our unknown. This is a really easy problem. We can simply plug values in and chug the problem away on our calculator. A nice plug and chug problem. We can put mass in there. We can put our acceleration in there. When we do that, we have force equals 0.06 kilograms times 5,000 meters per second squared. And we can simply punch those values in on our calculator. 0.06 times 5,000 equals 300. And our units are kind of interesting. Kilograms, meters per second squared are our units. Kilograms times meters per second squared. And if you'll recall, that's a Newton. So our answer, our force, is simply 300 newtons. So let's just think a little bit more about our nice equation here, force equals mass times acceleration. We have just a picture of a force from the hand accelerating this brick some amount. Some amount of force will produce some amount of acceleration. If I double the force and I use twice as much force, I'm going to get twice as much acceleration. Again, twice the force on twice the mass will give me the same acceleration. I know that because 2 times this amount of force and using 2 times that amount of mass will give me just the same amount of acceleration. So don't be afraid to think about your equations and think about their application to how things work. Also, don't forget that the net force is the sum of all the forces acting on an object. So when I have forces in different directions, my net force would be the sum of all of those. So we said Newton had 3 laws of motion. We know the first one is that objects resist change in motion. Remember the inertia idea, object in motion tends to remain in motion, and an object at rest tends to remain at rest. The second law of motion was the relationship between force, mass, and acceleration. And the third law of motion, you're going to have to watch the next video to find out. Advanced ideas. Show how you could derive Newton's first law by using Newton's second law of motion equation. See if you can think of how you might do that mathematically. Or diagram 4 forces acting on an ice skater skating forward. Explain why the skater can move forward for a long period of time. Why is that happening? So if you have other ideas too, feel free to go in depth for advanced proficiency, and I look forward to seeing what you have in class.